All right, let me get started. Sorry, I had somebody show up to office hours, right? Well, after office hours. So, in any event, I will begin. I will attempt to begin. Heavenly Father, we thank you for this day again. I thank you for your students. Just ask you to bless our work today. Help us to glorify what we do and to enjoy the weekend, Lord. You know my prayer, Lord Jesus. Amen. All right. I owe you guys a pendulum example, as I have forgotten to do the pendulum example. This example is, it's near and dear to my heart because it reminds me, this is the simple pendulum. It reminds me of when I was in college and I had this problem on a test. So the problem goes like this. You've got this, pendulum bob. It's connected here by a very light rope. All right. And let's say it has mass m. All right. And it's initially sitting there at rest, right? And then you've got a bullet, or no, it's a cat. You have a cat. And it's, I guess I should be, maybe that's too violent. You have a cat. I'll just draw the head. And it has speed v naught, and it comes over here, and after the impact, it gets embedded in the mass. So little mass m, right? And then of course it imparts some energy to the big mass, right? And then what happens is the mass and the cat embedded in the mass, they swing up to a certain maximum height h, right? So of course we've got, m plus m, and let's suppose that it goes up here to height h, right? And this is a rope of length L, let's say. All right. So this very problem, of course, a more boring version of it without cats, was in my junior level physics class, and I think maybe that same test I stared at the paper for like 20 minutes, didn't know what to do. I'm like, and then finally I was like, oh no, 20 minutes have expired, I should really work. So I started writing madly, and somewhere in that madness, I solved this problem, and it only took me like a minute. And I was like, yes, I solved it. Because I'm like, oh, okay. 1/2 little m v naught squared. Gravity's a conservative force, right? All that's going on here is gravity because the tension force is perpendicular, right? So 1/2 m v naught squared should be equal to m plus big M gh, right? So therefore, h is equal to 1/2 m v naught squared over m plus big M g. And I was so proud of myself. I'd solved this problem in like 30 seconds. I was like, yes. And then I was confidently walking out of the test. And then I foolishly talked to Somber Paul. I don't talk about Somber Paul as much, but there's also a Somber Paul. There's a Crazy Paul and a Somber Paul. Somber Paul was very good at physics, very good. And I said, I think I got that problem. I used energy conservation, and Sommerpaul said, and momentum conservation, right? And I was like, no. And I did not use momentum conservation, which is why I lost 50% of the credit on this solution, which was very generous at the point of the professor. I would take more like 70% off for this. So this is not right, because I'm ignoring the fact that in a collision, momentum has to be conserved, right? So we have to think about another step in this story, which is the moment right after the cat gets embedded here, right? Just right after the collision, there's an initial speed v1 for m plus m, right? I have to conserve momentum to before and after the bullet hits. Yeah? And that was my error on the test. But it's not an error you guys will make if I was to give this problem, right? Okay, so we have conserve momentum, which is mv naught is equal to little m plus big M v1. So I'm conserving momentum before and after the bullet's impact, right? Now momentum is not conserved in the upswing because of course gravity has time to change the net momentum of the system. But I have this, and now I can conserve energy in the upswing, right? And that looks like what? That looks like 1/2 m plus big M v1 squared. That's my initial kinetic energy, all right? And then what? Equals to m plus, this is why I got half credit. I was half right, you know? But I'm not as nice as my professor, so I'll take off like 70% credit, you know? I'm just joking. I might take off 80%. I don't really know. I'm just talking. Yeah. Okay, so and now we just have to solve for h. Yeah. So that's easy enough to do. Take the first equation, solve for v1 is mv naught over m plus m, right? Which implies that we can. Yeah, let's cancel these m's be canceling, right? And that gives me h is equal to v1 squared divided by 2g, which is actually giving me h equals to 1 over 2g times m v naught over m plus big M quantity squared, right? So there you go. That's the, you might call this the purely inelastic ballistic pendulum. Right. Of course, to put my example into practice, you need to find a cannon that you can fire cats out of or whatever, you know, in a reasonably large pendulum bob for which a cat could be embedded in. These logistics aside, it's a reasonable physical example. Maybe that's a little bit too much to say. So this is like one of the homework problems, right? Part A, where I give you a mass, it slams into the other mass, it sticks, right? Part B, though, says to assume that the collision of the bullet and the pendulum bob are elastic, right? That wouldn't be this situation. If they're elastic, what happens? If the collision of the bullet and the pendulum bob is elastic, that means that they don't stick together, right? It's a bouncy collision, and you have to conserve kinetic energy in the collision in this initial step, before and after, right? And in the upswing, the cat in this, if the cat could somehow collide elastically, if we had an elastic collision of the cat and the pendulum bob, the cat wouldn't be stuck to the pendulum bob, it would bounce off, and then we would just have the initial upswing. So I'm not going to work that. I'll leave that to you guys. But this is the pendulum, yeah? So two things: conserve momentum in collisions, and yes, the simple pendulum is a conservative system in that, energy, basically the gravitational potential energy is conserved as it swings back and forth, right? And converted, basically, all of the energy. Why didn't I have why didn't I have 1/2 m plus m, Vf squared here? Why? Right, all of the energy was potential. The kinetic energy at the top of the swing is 0, right? That's where it gets to its top and then it swings back, yeah. Okay, so any questions then? I'm going to go on then. If there aren't any questions. Nobody's got questions? All right. So the next topic is rotational motion. And I thought it would be good for me to start that today so that we have a little bit more time on it, because I think I've done a pretty decent job of telling you most of the main things about momentum already, so we might as well move on. Let's see here. I'm going to talk about the two-dimensional case for a little while. And so basically the idea is, we've got motion that's around some circle essentially, all right? And so if we have radius r and we go over a little ds here, right, corresponding to a little d theta there, the situation is that ds is equal to r d theta along a circular arc, right? So this tells me, among other things, that like ds dt is equal to r times d theta dt, assuming what? R is constant, yeah? What would ds dt, though, be? This would be the tangential speed, right? So typically we say something like v is equal to r omega. So this right here, we're talking about tangential speed angular velocity. All right. And this is the radius of the circular arc in question. So if that's the situation, what happens if we're continuing to move along a circle? What would happen if we differentiate this? What would we get? Differentiating, I get dv dt is equal to r times d omega dt. Why is r not varying? Listen, I'll deal with the possibility that r is varying next, all right? But to start with, I'm just thinking about a circular arc for this initial story that we're telling. So dv dt is to say the tangential acceleration. The tangential acceleration is equal to the radius times alpha. All right. Here alpha is equal to d omega dt, which is d squared theta dt squared. It's the angular acceleration. Aw, man. Well, I haven't hit a student in a while. think technically the roof hit the student, right? Did I hit one of you? Hit the table. Okay, phew. My record remains on. I know. I need taller ceilings, you know. So thank you for the assist. So the tangential acceleration is the radius times the angular acceleration. The tangential speed is the radius times the angular velocity. And of course, at the base of everything, if you were to integrate this, we'd have that the change in arc length is equal to r times the change in theta, right? That's actually the basic thing, is that the arc length subtended is equal to the radius times the subtended angle, right? This is essentially the definition of radian measure. So this is all two-dimensional stuff, right? So let me go through some calculus here. If alpha is equal to alpha naught, which is constant, then we have omega is equal to omega naught plus alpha naught t. And we also have that theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. How do I get those? I integrate and fit the constant, right? Integrating once gives me the omega formula. Integrating twice gets me the theta formula. What else do we know? Anything else going to be true in this wild world of rotational kinematics? Ooh, yowzers. How about this? Omega f squared, what should it be equal to? How about omega naught squared plus what? Two, yeah? 2 alpha naught change in theta. We have a winner. This, of course, is our beloved timeless equation, but now in the angular context. Anything else we know? How about this? You remember this one? People forget about this one, but the change in theta over the change in t is equal to the initial angular velocity plus the final angular velocity divided by 2. This is the average velocity is the average of the velocities relation. The average angular velocity, rather, is change in theta over change in time. The average of the angular velocities is theta naught plus theta 1 divided by 2. Or if you like, omega initial plus omega final divided by 2, right? Everything I just put in the box. Something very important to notice about the things in the box. They have a what? A condition, a presupposition, right? That presupposition is important, and if it's not true, these formulas do not apply. This constant acceleration is key, right? That's key. So let's see here. Example 2. Suppose a millstone with radius r. I'm going to use, oh fine, r equals to, I don't know, 0.7 meters. Takes 10 seconds, no, let's say 100 seconds to slow to a halt. If the millstone is spinning at, let's say, 200 revolutions per minute, RPM as it's sometimes called. Then find, let's see here, A, the angular acceleration, B, the net change in theta for the wheel, all right? And C, the number of revolutions made as it slows, grinds to a halt. All right. So this problem introduces some difficulties of rotational motion that we have to deal with. Sometimes we talk about radians, sometimes we talk about revolutions. What's the difference between a radian and a revolution? Well, a revolution is full circle, right? So like, let's start out with this pesky 200 RPM. That's my initial angular, velocity of 200 RPM. So 200 RPM doesn't really help me. 200 revolutions per minute, that's something I can work with algebraically. Because it's a revolution per minute. That's what RPM is. Oh, come on. Seriously? Just a second. Let me answer it. There we go. So 200 revolutions per minute. And well, they actually picked up this time. Come on. They don't usually pick up. I said it won't shut off. Go away. There must be some kind of like dust in the markers that's keeping my fingers from working. Anyway, so 200 revolutions per minute. It's like a telemarketing thing. 200 revolutions per minute. How do I convert this? I want to work in these formulas, they're all radians per second, all right? We must work in radians per second for these formulas to be true. It's, if I wasn't to work in radians per second, then I'd have to be really careful to convert everything to revolutions, and I don't want to do it because eventually, some point or another, we're going to go back and ask a question that requires us to work in radians. Let me think of a question that would require that, like part D. A string winds around the stone as it decelerates. How long is the string? There we'll need to use radius for sure. All right. Okay, so how do I convert revolutions per minute to radians per second? I just simply, first of all, how many revolutions is a radian? Yeah, 2 pi radians is 1 revolution. So I'm just multiplying by 1 there. All right. And then how do I convert minutes to seconds? Well, that's easier. All right. Minute is 60 seconds, I think. All right. Now I need to find a calculator. Yeah. We got here 200 times 2 times pi divided by 60. I've got about 20.94, something like that. I'll keep one more digit for good measure. 20.944 radians per second. All right. Now, how can I figure out the angular acceleration? How do we figure that out? Alpha naught equals to what? We could use omega f minus omega naught divided by, the time that it took. So my omega f is what? Yeah, the final angular speed is 0, right? It stops. So we've got 0 minus 20.944 radians per second. And how much time did that take? I think we said it took 100 seconds, right? So that gives me a negative angular acceleration, which I think makes sense because it's slowing down, right? It's kind of sad that I got a calculator to do this. That's not a good sign. We really should not need a calculator for this calculation, right? 0.20944 radians per second squared. Don't tell the other math professors. I'm just Mr. Cookin here. So anyway, yeah. So there's my angular acceleration. There's the answer to part A. How about the net angular? How many radians does this wheel spin through? You know. Right? It's spinning like this. Let's say the initial speed is omega naught, right? How many? So we're like, measuring a point here, and it's going like that, something like that. All right. How many times? What formula should I use for that? What do you guys think? The which one?
The boxed one.
Oh, the boxed one. Okay, yeah. That's usually a good idea. I think we got two choices, right? We've got enough information. We could either use the one right above the boxed one, or this one. Like either one would be fine. But I'll solve that for delta theta, which is omega f squared minus omega naught squared divided by 2 alpha naught, which is minus 20.944 radians per second quantity squared. Actually, I got to be careful. There's two different minuses going on here, right? There's the minus inside the square, which gets eaten by the squaring. And there's the minus outside the square, which is just minding its own business out there, and it survives. It's not being squared. Of course, omega f is 0, and downstairs we're dividing by twice minus 0.20944. The alleged survival of the minus upstairs was greatly exaggerated because, of course, it's getting killed by this minus in the denominator. Sorry, everything's so violent today. I guess my class is always violent. Let's see here. Times a 2. Invert that thing. Multiplied by 20.944. I mean, we could do algebra to simplify this further, but I'll just use the calculator because I'm being lazy. Anybody else get 1047.2? And what are the units on this thing? Not degrees. Yeah, so we got radians squared over second squared upstairs. I have radians over second squared downstairs. The second squareds cancel, and we're just left with radians, as we ought to, since we're calculating an angle in radians. So there you go. That's the net change in angle for the wheel. That's the answer to part B, right? How about C? So the number of revolutions, right? So we take the change in theta and we divide by 2 pi. And what's that give me? One 166, say 0.7, something like that, revolutions. I usually just abbreviate revolutions rev. So there's the answer to part C. How would we figure out part D? The change in arc length, right? That would be the length of the string that wound around it, would be literally the arc length that's been subtended by a point on the the edge of the wheel. We're assuming that the string is infinitely thin, so it's not like it's all at basically the same radius, the outer radius of the millstone that we're winding around. So not like a yo-yo where the string actually wraps on top of itself and gets bigger or smaller, right? All the same radius. This 0.7 meters. Notice that we have not even used 0.7 meters up to this point. Not once, right? Because everything else here that we've asked about was purely of an angular nature. Now we're asking a question that interfaces the radius to the angle subtended. And so there we're bridging the gap between the angular and the linear, and the radius matters for such a question. So the answer is simply r times delta theta, which is 0.7 meters times my 1047.2 radians. I won't write the radians this time because we don't need to. Let's see here. 47.2 times 0.7. I get, whoa, that's a lot. 733.04 meters. That's yeah, I guess that makes sense. Does it make sense? What's the circumference on this thing? 0.7 times 2 pi, right? So the circumference is 4.4 meters. So you take 4.4 meters times 166.7, and you get, 733.04 meters. So yeah, that's right. That's right. Checks. By the way, there's another way you could have done this, right? Another way you could have calculated the net length of the string would be to take the number of evolutions times the length of one revolution, which was 2 pi r, right? That's another way you could think about this, but it's good to think of it this way. And any questions? So you notice in this problem, we have not yet given an account for why or how the millstone is slowing down. I just told you that it did. This is like the problems we worked at the start of the class, which were kinematic, right? We haven't given a reason for the millstone slowing down. The answer, of course, later is going to be there's some kind of friction force, and it breaks. It's breaking the wheel, like a car brake, and that's slowing the wheel, right? And when we take ultimately, the viewpoint we want to take is that the millstone actually has angular momentum. And that angular momentum is lost as a torque is applied to the wheel. And as that torque decelerates the wheel, the angular momentum goes to 0. That's the ultimate viewpoint we want to get to. We're not there yet, obviously. Yeah.
So did we just assume that the angular acceleration was constant for this?
Yes, because we don't have enough information to do otherwise. And you're right. I should say find the alpha assuming constant alpha, yeah. If I didn't assume constant alpha, I couldn't answer those questions. That is true. Now, does it have to be constant? No. But if the angular acceleration is not constant, then what do we have to do? What do we have to do if the angular acceleration is not constant? So like your example 3, given that the radius is equal to a constant r, and alpha as a function of time is equal to, let us say, t squared plus b times the cosine of gamma t, right? Find omega as a function of time and theta as a function of time, given that omega of time 0 is omega naught and theta of time 0 is theta naught. This problem, we obviously cannot use the constant acceleration formulas constant angular acceleration formulas because the because the angular acceleration is not constant, right? That's kind of our clue. So what do we do? Integrate. Yeah, we just do calculus. So I'll start us out here. Alpha is d omega dt, but it's also at squared plus b cosine gamma t. I'm assuming, by the way, guys, here that a, b, and gamma are all non-zero. Well, they're constants anyways, more the point. These are just constants. So integrating this gives me what? Omega of t is equal to 1/3 at cubed plus b over gamma sine gamma t plus some constant, right? I'll call that C1. Now is C1, is it 0? What is it? Like, well, here's the deal. Omega of 0 is what? What happens when we plug 0 into the soon to be underlined in green formulas? That's all what? 0, right? Now we need to think through this. Many of you lost many points needlessly, right? By not checking this simple thing in the calculus in the previous test. When we plug in 0, do we really get 0? I had a cosine in the test. I got a lot of you, because if you didn't put 0 in, you didn't see cosine of 0 is 1, and that affects how the constant's fixed, right? So don't let me get those points on the final. Like, keep those. I don't want them. You keep them. So that is C1, because this part's 0, and we just get C1 equals to... So this time C1 is indeed omega naught. So therefore, omega at time t is in fact omega naught plus 1/3 at cubed plus b over gamma sine gamma t. All right? So there we go. We found our angular velocity as a function of time. Next up, we need to find the angle. So remember that omega is equal to d theta dt, which is equal to this, which implies what? Theta is equal to, theta as a function of time rather, is equal to, I integrate omega naught t, I integrate, I get plus 1/12 at to the 4th, right? And this guy, I get minus b over gamma squared cosine gamma t plus c2. Right? Now this time it's a little bit more exciting in some sense because the constant, we actually need to really think through it a little bit better. If I look at theta of 0, what do I get? I'll write it out. 0 plus 0 minus what? Is cosine of 0 is 1, right? So that term actually gives me minus b over gamma squared, right? Plus c2. What is c2? Well, now we can figure it out. See, because this all has to be equal to theta naught, that was given. So my c2 is apparently theta naught plus b over gamma squared. And we can put it all together. We get theta as a function of time is equal to theta naught. Oh, okay. Theta naught plus omega naught t plus 1/12 at to the 4th. And I decided to go ahead and package my b over gamma squared terms all together. Namely, I've got 1 minus a cosine of gamma t. And there you go. And you can check my answer, right? Check my answer. Plug in times 0, what happens? It just equals theta naught, right? Because the terms with t are just 0. But the term with the cosine, we get a 1 minus cosine of 0, which is also known as 1 minus 1. And so we get exactly just theta naught when we plug in times 0, which is what we want. So nothing really new here, guys. It's just that now we have to work with what? We've got alpha is d omega dt, and omega is d theta dt, right? And theta is equal to the angular position. But otherwise, the song remains the same in terms of like the calculus that we did, right? Any questions? Let's see here. Let me, I said I'd talk a little bit about how to understand this if the radius is not constant. So let's think about that a little bit. What if the radius, we're still going to just focus on 2 dimensions today. I won't go, I mean, you can talk about rotations in 3 dimensions, and indeed we will, but not today, all right? So what if we're in 2 dimensions, right? And we've got some trajectory, right? And I want to talk about this trajectory here in terms of the radius from the origin and the standard angle theta. We could do that, right? Whatever we work out for that, it ought to reduce to what we've already done if we consider the case of motion, which is circular in some sort of circle concentric about the origin, right? But we'll discover more in terms of the relation between, say, polar coordinates and Cartesian coordinates. How do we figure those out? It's actually pretty easy, guys. We just write down x is r cosine theta, and y is equal to r sine theta. Everybody knows this, right? Like your little brother or little sister in 8th grade, they learned this already, right? They should. Like, I'm an only child. Fine, I accept that. You should have learned it in 8th grade then. But anyway, so whenever you learn this, if we differentiate this, x dot is r dot cosine theta minus r sine theta, theta dot. And y dot, it is r dot sine theta plus r cosine theta, theta dot. If you're wondering, r dot is equal to dr dt, and theta dot, it's equal to d theta dt. These are just notations for time derivatives. These notations go back to Sir Isaac Newton. Did I ever tell you about Sir Isaac Newton's prophecy? You know, he spent the lion's share of his time not studying physics, but actually studying revelations, and he had vast writings on prophecy and so forth. He was actually not a Trinitarian. He was what's known as an Arian. He believed in God the Father. So he had certainly, what would you call, heterodox views for today. Like very few people would share his beliefs. But he also had a belief basically that everything was thrown into chaos after the Trinitarian heresy came into play around the year 400. So all of his interpretation of Revelation was based on this, basically seeing bad guys behind the corners in terms of the Trinitarian heresy. But one of the interesting things he predicted is that around the year, around the turn of the 20th century, around the year 1900, there would be a push for Israel to reunite as a nation. And that he also prophesied that, if I recall correctly, that Israel would become a nation in 1948. So that's a little bit disconcerting because those kind of both happened. And then the other thing is the end of history as we know it, the end of human civilization and existence is like in, I'm trying to remember if it was 2030 or 2050. It's a little bit in the future to us, but not much according to Isaac Newton's prophecy. So, yeah. But his physics is really good.
I think
Physics is really good. The story of these writings is very interesting. Like very elite libraries, British libraries, refused these writings. If I remember right, I think Cambridge would not accept these writings of Newton's because they were not of a physical nature. And I think they thought it would like sully his reputation or something like that. I don't know. So the story of these extra writings of Newton and how they were handed down in different estates and stuff, it's actually quite fascinating. But oh, I'm sorry, I was doing this. So the speed squared is x dot squared plus y dot squared. No one cares about Newton. Let's get back to physics. So if you look at that, this simplifies to r dot squared plus r squared theta dot squared. Because when you square these, you get r squared cosine squared, r dot squared sine squared plus cosine squared is 1. And when you square these, you get r squared sine squared, and an r squared cosine squared times a theta dot squared. Sine squared plus cosine squared is 1. That gives you this. And the middle terms, you get a twice r dot theta dot sine theta cosine theta, and a twice r dot theta dot r sine theta cosine theta. But one's got a plus and one's got a minus. They both got a 2. They'd be canceling. You just get this. But this, if you recognize, is the radial velocity squared plus r squared times what? Omega squared. So the formula for the speed squared in 2 dimensions in terms of polar coordinates is this. In the case that we have constant radius, what do you have? What's VR when you have constant radius? If r is constant, r dot is 0. And so the speed squared is simply r squared omega squared, and we're back to where we were earlier today, namely that v is equal to r omega. But please beware that this is only for a circular arc, where the radius is not changing relative to the origin of the system you're thinking about. So yeah. And then if you want to find the formulas for acceleration, well, that takes us back earlier in the semester. I worked those things out in terms of the curvature and the radius and the Frenet frame. Remember that? We worked that out earlier. The formula we worked our way to was that the magnitude of the acceleration squared was equal to the tangential acceleration squared plus well, the normal part of the acceleration squared, right? And that is d squared s dt squared. That's the formula for the tangential acceleration. And the normal part was, well, we could write it as v squared over r, right? Quantity squared. But if we write that in terms of the angular velocity, what's the formula for acceleration then? How do I write v in terms of r omega here? So that would be like so I guess I should use little r at the moment. My bad. So I got an little r omega squared over r squared, which is ds dt squared. That's supposed to be d squared s dt squared squared. My bad. Too many squares. And I think that is going to simplify to r squared omega to the 4th. So let me just seal this in for posterity. The formula for acceleration is the tangential part of the acceleration squared plus r squared omega to the 4th as it happens. Every so often you need that in this material, but it's kind of a rare Pokemon. Sorry about that. Let me fix this. There you go. Sorry, I should have done that like an hour ago. Have a good weekend. You don't have to go home, but you can't stay here.